Okay, so let's start the class. So today we will continue the discussion on number theory, and then we will talk about a new type of symbol called, a new type of arithmetic called modular arithmetic. So basically we will introduce this notation. So if you look at this, you have a A, and then you have a symbol which looks like equal, and then a B, and then bracket modulo n. So it reads as A is congruent to B modulo n. So congruent means the same. Okay, if you have two triangles that is exactly the same with the same length, same size, same angles, then it is called congruent triangles. Here we are looking at integers. We are saying that integer A is the same as integer B under a certain type of scenario. We call it modulo n. So what does it mean? It means that, so when we try to divide this A minus B by n, then you can divide this properly. So n can divide A minus B properly. Is that okay? So to try to remember this, yeah, perhaps I would give you this fact. Okay, this is perhaps the best fact. Oh, so let me give you some example. So for instance, you will say 29 is congruent to 15 modulo 7. It is because the difference between 29 and 15 is a multiple of 7. Is that okay? So we can say 29 is congruent to 15 modulo 7. Or we can also say 4 is congruent to 3 modulo 1. But of course, it will be true for any integer modulo 1. Is that okay? So normally, we don't have a 1 here. Is that okay? Okay, so how to memorize this? So perhaps let's look at this fact. Okay, so the first one is, for an integer A is going to be having the same as, so A is going to be congruent to A modulo n, taking the remainder after dividing by n in this world, A mod n. Okay, is that okay? Okay, so the proof is actually very simple. So here, so the proof is, suppose we can write down A as some Q times n plus R, with R is an integer between 0 and A minus 1. Then we will have R is, by definition, the value of A modulo n, right? Is that okay? So we have A minus A modulo n will be equal to A minus R, which is equal to Qn. Okay, so n, so thus n divides A minus A modulo n, and we have the result there. So A and A modulo n will be congruent to each other under this mod n world. Okay? And then similarly, we will also have the second one. So if A is the same as B under modulo n, this implies the remainder of A is the same as the remainder of B when you divide it by n under modulo n. Okay? Okay? Is that okay? So for this one, you can also prove this easily using this definition. So you write down A is equal to Qn plus R, and B is equal to Q prime n plus R prime. And then by this one, you get the fact that R prime has to be equal to R. So in that case, we'll have this one equal to this one. Is that okay? So this is going to be easy. So in that sense, so we can interpret this in a different way. When we say A is congruent to B modulo n, one way, this is by definition, n divides the difference. But the other way is that these two numbers will have the same remainder after dividing this by this number. So when 27 you divide it by 7, when 29 you divide it by 7, the remainder will be equal to 1, right? And then 15, when you divide it by 7, the remainder will be equal to 1. Okay, so it just says that if A is the same as B modulo n, then they have the same remainder after dividing by n. Okay? Is that okay? Good. Then, with this in our heart, then we can have a lot of lemmas proven easily. So for instance, we can prove this one. A number is the same as itself when you take modulo n. Oh, of course, it's the same, right? So you divide by n. This side has certain remainder. This side has certain remainder. The remainder has to be the same. Is that okay? Okay. You can prove this by using just the interpretation that we have, or you can prove this based on the definition. Because the definition is A minus A is going to be 0. N divides 0. So A is congruent to A modulo n. Okay? So we can also have this one. Suppose that A is congruent to B modulo n, then this will imply B is congruent to A modulo n. Okay? And this is actually trivial. It says that A and B have the same remainder after dividing by n. So it says that B and A have the same remainder after dividing by n. So this must imply this one. Does that make sense? Yeah, we don't need to prove it, but you can prove it always by definition. So we can also have the third one. Let's say we know that A and B have the same remainder after dividing by n, and we also know that B and C have the same remainder after dividing by n. Then these two will imply A and C is congruent. Is that okay? Is that okay? Now actually, this 3, 4, 5 shows that. So this shows that this operator, you can think of this as a kind of a relation, right? It relates whether two numbers are related or not. So a number is related to itself. So this type of property, we call it a reflexive property. So it's like a reflection. Is that okay? And then this one it says that, okay, A is related to B, then you can switch it. B is also related to A. Now this is a kind of property called symmetric. Notice that not all the properties in the world are symmetric. So the less than is not symmetric. A is less than B. It will imply that B cannot be less than A. But on the other hand here, this relationship A is congruent to B implies B is congruent to A. So this is called reflexive. Is that okay? And then this is like A is related to B, B is related to C, and then it implies A is related to C. This property is called transitive. And then if a relation has reflexive, symmetric, and transitive property, then this is a special type of relation. This is called what? Equivalence relation. So emphasize here not all properties are transitive. Not all properties are reflexive. So for instance, less than is not reflexive. I am not less than myself. Okay, 3 is not less than 3. Okay, but less than is transitive. A is less than B, B is less than C, C, then A is less than C. But then some relation may not be, like A likes B, B likes C, then it doesn't mean that A likes C. Okay, maybe A and C are enemies. It could be something like this. Likes in general is not transitive. Okay, but here this relation is transitive. Now, when we have properties of these things, then this type of relation, we call it an equivalence relation. Equivalence relation, just in our heart, it means equal. So you can replace two things that are related in any way that you like, because they are equal. And then, so we will see that. So in what case we can do this replacement? So there are some situation we can replace easily. Okay. So okay, actually, the property of having an equivalence relation is that you can partition the number into different groups. So under a certain scenario, for instance, suppose that we are going to talk about modulo 3. Is that okay? Modulo 3. Then what things will be equal? Okay, 0 will be equal to 3. Am I correct? Okay, and then 0 will be equal to 6. Is that okay? And then 0 will be equal to, so think of this as equal to minus 3. Is that okay? But then 0 is not going to be equal to 1. So they are not equal. But on the other hand, 1 is going to be equal to 4. 1 is going to be equal to minus 2, and so on and so forth, right? So if you think of the numbers, all the integers all together, so you can actually group them together if they are in the same group. So 0 is going to be equal to 3, so they are going to be put into the same group. Minus 3 is also there, 6 is also there, minus 6 is also there, and so on and so forth. So there's a group here. And then we can also have another group. This group is like 1, 4, minus 2, 7, minus 5, and so on and so forth. So there is another group. And then we will have another group 2, 5, 8, minus 1, minus 4, and so on and so forth. Okay. So with an equivalence relation, we can always partition the items that we want to consider, the integers here, into different groups. Each integer belongs to one group. Is that okay? Okay. Now, so equivalence relation relates to partition. And more. Okay, in modular arithmetic, it has also a lot of interesting results. So for instance, we will have 1, 2, 3, 4, 5. Okay, so we can have the result number 6 here. Let's look at it. So for instance, suppose that we know that two numbers are the same when you divide it by n, so the same remainder. Then this implies what? This implies that if we add the same number to them, then it will still be the same. They are still congruent to each other. Is that okay? Is that okay? Okay. And actually, this direction is, you can go back. You can go back. If you have A plus C is congruent to B plus C, then A must be the same as B. Why? So you add the number, let's call it minus C on both sides. Then you cancel the plus C. You get A is equal to B. Is that okay? So this is okay. We can have another one. So suppose that you have A is equal to B mod n. Then this implies A times C is equal to B times C mod n. Okay? Is that okay? Now, but on the other hand, this direction, you cannot go back. You cannot go back. For instance, in general, you cannot go back. For instance, you have 14. 14 is equal to what? So this equal is the arithmetic equal. So 14 is equal to 7 times 2, right? And then 14 is equal to 4. mod 10. Is that okay? So 14, so this mod talks about this thing. This equal is the natural arithmetic equal, okay? So 14 is exactly equal to 7 times 2, okay? 4 is equal to 2 times 2. So you have this one, but you cannot go back. Because 7 is not the same as 2 mod 10, okay? Okay, so you cannot go back for this one. But for addition, you can go back. Subtraction, you can go back. Multiplication, you may not be able to go back. And what's next? The next is, okay, so this is going to be easy. So suppose that this time A is the same as B, mod n. And then we have also C is equal to D, mod n. Then what? Then we will have A plus C is the same as B plus D, mod n. Is that okay? And then what do we have? We also have A times C is equal to B times D, mod n. Is that okay? So this one, you can apply this twice, okay? A is the same as B, C is the same as D. So A plus C is the same as B plus C. Is that okay? Does that make sense? And then B plus C, because C is equal to D, so B plus C is equal to B plus D. So you have B plus D. Is that okay? So how to prove this? So A plus C is the same as B plus C. Am I correct? Because you add the same number. You have A is equal to B. So when you add the same number, they're the same, right? Is that okay? Is that okay? And then B plus C is equal to B plus D. The reason, because C and D are the same. You add the same number B, so they will be the same. So that's why this one is the same as this one. Is that okay? So here, it is the same. So AC is equal to BC because you are going to multiply with the same number. Because A is the same as B, you multiply the same number, you will have AC is equal to BC. Does that make sense? Okay, but on the other hand, you can see that these two are also the same. You have C is equal to D. When you multiply with the same number B, then they will be the same. Is that okay? So 8 is what? It's a little bit slightly general version of 6 and 7. Okay, but here what we can see, okay, we can see is that when they're the same, then in a formula you can replace the same thing by replace one thing by the same thing. So you have A and C here. Okay, now I know A is equal to B, so I can replace A freely as a B here. Because I know C is the same as D, so I can replace C as a D here. So I will have B plus D here. Is that okay? And similarly, you can replace this one in also a multiplication formula. Is that okay? So that explains, okay, that actually indicates the power of modular arithmetic. What we care is whether two numbers have the same remainder. If they have the same remainder, you can treat them as the same number in this modular world. Okay, so this is the key point. Okay? Okay, now, but so far, so this is about addition or subtraction. Subtraction is the same as addition, right? This is about multiplication. But in modular arithmetic, we don't have division. Okay, we don't have division. We can have a restricted type of division. So let's see. Okay. So this is a special case that we can have division. So we have a theorem. Suppose that we have BC is the same as BD under this modulo n arithmetic, and we also have B and N does not have any common divisor, the GCD of B and N is equal to 1, then we can cancel. We can do cancellation. Then we can have C is the same as D modulo N. Okay? Okay. So for this, let's, okay. So this is an important thing. So when, okay, it's not if and only if, it is just if it happens. If B is having no common divisor with N, then we can cancel B on both sides in a multiplication formula. Okay, but it doesn't mean that when you need to do canceling, it has something like this, okay? But it just says that when this happens, you can cancel. Okay, so let's have a proof. So we can prove this in two different ways. One is by definition, and the other is by the property of GCD that we have studied. Okay, so proof number one. Proof 1. Okay, version 1. Okay, so how do we prove this? So back from definition. So we know that N divides BC minus BD, right? From this. Okay. So N divides B C minus D. Is that okay? But then because this GCD of B and N is equal to 1, we have done something before. N will not be able to divide this B. Actually, it's unrelated to this part. So N will divide C minus D. Is that okay? So therefore, because therefore, this implies, or this means, C is the same as D modulo N. Okay? Is that okay? Is that okay? So this result is what we have done before the exam. Okay?